we were discussing the Schwarz space, and then we said that it's very congenial with respect to the Fourier transform. So let us prove the following theorem. Let f belong to S of Rn, then f hat belongs to S of Rn as well. Further, the map f going to f hat is a continuous linear map of S of Rn into itself. So proof. So we will do it in some steps. So step 1. So let f belong to S of Rn, then f belongs to E of Rn. So as a first step, if it's going to belong to S of Rn, it better belong to E of Rn. So we are going to show first that if E of Rn. So Ek is the standard kth basis vector in Rn. So what is Ek? Ek is 0 etc. 1 in the kth place and 0 elsewhere. Okay. So for 1 less than or equal to k, less than or equal to n. Okay. Then f hat of xi plus hek minus f hat of xi by h. So we are trying to find the kth dx by dxk, dxi by dxk of f hat. So that is what we are trying to do. So we want to first find out what is this quotient. So this is equal to 1 over h integral over Rn e power minus 2 pi I x dot xi plus hek minus e power minus 2 pi I x dot xi multiplied by fx dx, and that is equal to, we apply the mean value theorem to this differentiable function. So what is this? This can be taken as the derivative at some intermediary point. So what is the derivative? That is minus 2 pi I times integral over Rn e power minus 2 pi I x dot xi plus theta h ek times xk f of x dx. Okay, so this is just, I have just differentiated e power 2 pi I xi with respect to the kth value xk. So I get x minus 2 pi I xk here, and that is what we have here. Okay, where 0 will be less than theta less than 1, and it will depend on x and h. Okay, so now the integrand converges to, that is pointwise, e power minus 2 pi I x dot xi xk fx as h goes to 0, and it is bounded by, so modulus of this exponential here is just 1. So mod xk fx, but f belongs to S of Rn. So xk fx is also in S of Rn you are just multiplying by a monomial, and that of course is continuously embedded in L1 of Rn. So this is integrable, it converges pointwise. So by the dominated convergence theorem, you have that the limit. So if you take the limit on the left hand side, that will give you df hat by d psi k evaluated at psi, that's equal to minus 2 pi I times integral over Rn e power minus 2 pi I x dot psi xk fx dx. And xk fx dx, as we already saw, belongs to S1, so that's in L1. So this is the Fourier transform of some function. So RHS is the Fourier transform of a L1 function, namely xk fx, and hence is in fact uniformly, that's not necessary for the moment, continuous. So we can iterate this, iterating we get for all alpha multi-index, you have d alpha of f hat of psi. So each time you differentiate, you will pick up minus 2 pi I. So minus 2 pi I to the mod alpha will come, and then each time you have to multiply by a monomial corresponding to x. So you will get x alpha, x power alpha f of x hat psi. So if you want to differentiate the Fourier transform, you first multiply the function by a corresponding monomial and then take the Fourier transform. That is it. Now we have the dual, so this implies, and this is uniformly continuous. So this implies that f hat belongs to E of Rn. Step 2. Okay. So we will show two pi I psi j f hat of psi is nothing but df by dxj hat at psi. Okay. So this is nothing, which is by definition df by dxj is again in S, because it is just a derivative of S function. So this is again integral over Rn e power minus 2 pi I xi df by dxj at x dx. Okay. So you see the duality here. So when you want to differentiate the Fourier transform, you multiply the function by a monomial and then take the Fourier transform. If you want to differentiate the function and take the Fourier transform, then you take the Fourier transform, multiply by a appropriate monomial. So this is the duality between these two properties, and so now this is essentially a consequence of Green's theorem or the integration by parts. So we have df by dxj belongs to S of Rn and hence in L1 of Rn. Okay, and so we have by the dominated convergence theorem, we get, so by the dominated convergence theorem, so you get that integral over Rn of e power minus 2 pi I x dot psi df by dxj at x dx is nothing but the limit as r tends to infinity, the integral over the ball center origin radius r e power minus 2 pi I x dot psi df by dxj x dx. Okay, because you think of this function as the integral over Rn with chi of 0 or chi of this ball multiplied here, then pointwise it converges to S, it is bounded by a integrable function. So by the dominated convergence theorem you get this. So we just have to look at this bounded domain integral and see what the limit is going to be. So, integral b0r of e power minus 2 pi I x dot psi df by dxj evaluated at x dx equal to integral over b0r of, so I am going to differentiate with respect to okay, so we have to differentiate. So you get a minus sign first when you are changing the derivative on this side, but when you bring back the, when you differentiate you get 2 pi I and you have to differentiate with respect to xj. So 2 pi I xi j is what you will get, e power minus 2 pi I x dot psi f of x dx. Okay, so this is what you will get, and yeah, so that's what you will get when you do the plus. You have a boundary term. Now what is the boundary term? That is integral over mod x equal to r, that is the sphere, of e power minus 2 pi I x dot psi into f of x into the normal, outward normal in the j direction, but this is a ball center origin and therefore the normal is just the radius vector, and you have to divide it, to make it the unit normal you have to divide it by the length of the radius. So you will just get the jth component of the normal is just xj over r d sigma x. Okay, so this is what you will get when you write Green's theorem. Okay, so now we will estimate this boundary term. So modulus of 1 by r integral mod x equal to r e power minus 2 pi I x dot psi f of x into xj d sigma x. D sigma x is the surface measure. Okay, so that is less than or equal to 1 by r into integral mod x equal to r. We can forget the e power minus 2 pi I, its modulus is 1. So mod xj mod fx d sigma x. Now we are going to write this is less than or equal to mk by r into integral mod x equal to r xj mod xj into 1 plus mod x square to the minus k d sigma x. What have I done? I multiplied and divided by 1, I multiplied by 1 plus mod x square to the k and 1 plus mod x square to the minus k, and we have that mod fx into 1 plus mod x square to the k is less than mk. This is the Schwarz space property since f is in S of Rn. And you can choose any k you like. Okay, so this constant k, number k is independent. Now we can choose whatever we like, and therefore you have but what do you know about mk by r? Integral mod x equal to r mod xj into 1 plus mod x square d sigma x is equal to mk, this is power minus k, sorry, by 1 plus r square to the k into r, okay, and integral over, I will change the integral to mod y equal to mod x by r is nothing but mod yj, okay, x by r equal to y, and then d sigma x will become r power n minus 1 d sigma y. Okay, so because that's how the thing will change. Okay, so you have d sigma x will just become r power n minus 1 d sigma y, which is the surface measure over the unit ball. So now this is a constant, mod yj is integrable function, and then this will tend to 0 as r tends to infinity if k is large enough. And we have the freedom to choose k, and therefore we choose k as large as you need. So this boundary term goes to 0, and then therefore you get therefore you have proved this result here. So therefore, so you have that 2 pi I xi j f hat xi is equal to df by dxj hat evaluated at xi. Okay, so we, as r tends to infinity, we have that. So step 3. So iterating, we get the 2 pi I xi to the beta. So each time you have to put the monomial and the 2 pi I. So 2 pi I xi to the beta f hat xi is equal to d beta f hat xi. Okay. So combining this with step 1, okay, so you get that xi beta d power alpha f hat of xi is equal to minus 2 pi I to the mod alpha by 2 pi I to the mod beta into d beta of x alpha f of x hat xi, and this again is in S of R. Okay, and therefore this belongs to this is and therefore this is bounded, equals bounded in R for all alpha beta, and this proves, so this implies that f hat belongs to S of Rn. Again, so step 4, let C equal to the integral of dx by 1 plus mod x square to the k d for k large enough. Then what do you have? We have that sup of xi to the beta of d alpha f hat xi is less than or equal to c times 2 pi I to the mod alpha minus mod beta sup over, so x in Rn or xi in Rn, and this is x in Rn, 1 plus mod x square to the k of mod d beta x alpha f of x. Okay, and therefore if fn goes to 0 in S of Rn, this will imply that f hat n goes to 0 in S of R, and therefore implies f mapping to f hat is continuous. Okay, so that proves the theorem continuously. Okay, so now we have the following corollary. This is called the Riemann-Lebesgue lemma. And there are several versions of this Riemann-Lebesgue lemma. So this is one way of stating it. So f is in L1 of Rn, then f hat is uniformly continuous, this we already saw, and vanishes at infinity. So proof. So if f belongs to S of Rn, this we have just shown that f hat belongs to S of Rn, implies f hat vanishes at infinity, and is in E of Rn. So it is in particular continuous and vanishes at infinity, implies continuous and vanishes at infinity. Implies uniformly continuous. Okay. So now let f belong to L1. So we already know that D of Rn is in S of Rn, and that's in L1 of Rn. So D of Rn is dense in L1 of Rn, so S is also dense in L1 of Rn. Okay, and consequently, so let Fn in S of Rn such that Fn converges to F in L1 of Rn. Then we have already seen mod Fn hat xi minus f of xi is less than or equal to norm Fn minus f in L1, which goes to 0. That means norm Fn hat minus f hat infinity is less than or equal to norm Fn minus f in L1, and that goes to 0. So implies Fn hat converges to f hat uniformly. So if it converges uniformly, that means f hat is continuous and vanishes at infinity. Because the space of continuous functions which vanish at infinity is a Banach space for the sup norm, and therefore f hat is Fn hat is continuous and vanishes at infinity because it's in S of Rn, and consequently f hat is also continuous and vanishes at infinity, implies it is uniformly continuous. Okay, so this is the Riemann-Lebesgue lemma.